teve uma introdução no meio, todas as guardas soltas, é isso?
Sim, eu tenho o Light Source
I can try to see if this should work. Let me try. And I sent out the link for the lab material last night. It's pretty late, and I don't think it's on the GitHub yet, but we can check during the coffee break on that.
Okay.
Yeah, I have the link. If Ariana can just send the link to everyone, that should be fine too.
Sure.
Yeah.
Oh, you're right. You're in. Yeah, do you want to put it on top? Because I'm going to
All right,
first
all right,
show
all right.
something.
Yeah, so I can just put
No, I'll hold.
Okay. Let me log in and at least it.
But the link is not on GitHub yet. But the link is not on GitHub yet.
So the
There might be a pull request. I might do it now.
okay. So it's not in rush because the first session is only presentation.
Yeah.
It's the link for the second link that.
Yeah.
Yeah.
But so Adriana will do that for you if you
Yeah.
send her. But I will do the pull request.
Yeah, I thought like Arun told Raul the other yesterday, but maybe someone probably already know that, but it's
Yeah, he did it already.
Yeah.
I know he did it, but the link might not be there because
All right.
requires a pull request, accepting a pull request. Can I?
yes.
Thank you. But it's there. It's fine. It's working.
Well, probably wait like people.
Yeah, maybe sit for a moment because I'll just do a brief introduction. Then Priyanka will introduce you,
Okay.
and then you'll come.
Yeah. So do you want me to just wait here, or I can?
Maybe sit. Yeah, you could sit there by Priyanka. Come this way because I'm going to talk for a minute, and then you introduce. Yes. Her. Podemos começar? Teste, teste. Teste, teste. Teste, teste, teste. Teste, teste, teste. No, no, it's really...
Estamos a preguntar quién es que era.
So, good morning, everyone. Welcome to day 2 of JuliaEO 26. We have a super interesting day again. Let me just a quick shout out to our sponsors again. Luso-American Foundation, University of Açores and the regional government, and the municipality here of Angra do Heroísmo. We might see someone from them with us for lunch during the week. So today, our focus is, we start with SAR. So we have insight theory, interferogram processing, and its application towards science studies. And then we have a workshop, INSAR workshop. Then Bonito and Mikey visualizations, METOP data, interactive analysis of large-scale geospatial data formats with Felix again, like as a succession of what was done yesterday, and a curious, provocative presentation, Julia on trial, and then a bit of out-of-the-box presentation about climate crisis and how societally we are dealing with this. So let's move on to the first presentation.
Good morning, everyone. Our first presenter is Ann Chen. She has more than 15 years of experience in SAR algorithm design for Earth system science applications. In 2017, she joined the Department of Aeroscience Engineering and Engineering Mechanics at the University of Texas at Austin. Since 2018, she has also served as a faculty member in the Department of Geological Sciences at UT Austin. She currently leads the radar interferometry group housed in the Center for Space Research. Her group focuses on the development of new satellites and especially interferometric synthetic aperture radar techniques for studying natural and induced seismicity, groundwater resources, natural disasters, and permafrost hydrology and carbon storage. She is a senior member of IEEE. I welcome N. Chen.
This one is better. It worked. Just
Yeah.
we can try the
This one is better.
Yeah. Okay. See. All right. Detected. Okay. Yeah. Good morning, everyone. And I'm Ann Chen. I'm from UT. So last year I attended the Julia workshop virtually, and it's a great pleasure to finally be here in person. So I am a radar scientist. So my group mainly do two things. So first, our group focused on developing radar processing algorithm, community-based software, and to make sure the code can handle the large volume of data and do that efficiently and fast. And the second thing we do is we don't typically just end in the processed interferogram. So our group student, typically each of them would lead to an application direction, and they are trying to use the data produced from the software to study the Earth. And so example the active subduction zone, earthquake and volcanoes, or groundwater aquifer pumping and related subsidence, and also coastal subsidence and the associated flooding risk due to the relatively sea level change, things like that. So I think I'm pretty fortunate to in this area because you can see that the applications span a very wide variety of disciplines, and I work with a lot of the other colleagues who taught me things we need to be able to advance science. But what is interesting is all those science are enabled by the code we wrote and the process. That's kind of the core of what we do in our group. So today I would like to give a brief tutorial to kind of the first session today is to explain how INSAR works. So that's kind of the theory behind our software. And in our second session, I will kind of give you an overview of the software processing strategy and also sample data set. And so I was mostly a Fortran MATLAB kind of person before knowing Julia. So I'm still very new, but I was able to assemble a package that gave you a demonstration what our data looks like and how you be able to read it, those binary data into your machine and then visualize it. And so if you can read one, and in a typical analysis nowadays, you can do thousands of them and then do a more complicated analysis. So that's the plan for today. So, and the theory session, I've mentioned that this lecture series is a part of a summer course I teach every year in the summer, organized by EarthScope, that is a National Science Foundation in the United States, founded a consortium. And so the lecture material was developed by many, many colleagues together. So I'm here just presenting that. Yeah. And so first, in order to do interferometric synthetic aperture radar, or INSAR, you first got to know SAR, because INSAR is kind of a subset application that the SAR enables. So is that automatically playing? So for synthetic aperture radar, the way it works is at a given time, a satellite, maybe even an airplane that fly over an area of interest. If it's on satellite, it's spaceborne. If it's on jet, it's airborne. The way it works is more or less the same. It's just how far away it is from the Earth. So at a given time, a radar or board on satellite flying over an area of interest, periodically it will send out radar pulses, microwave pulses along the sideway. So imaging radar is different from sounding radar or radar altimeter in case that the sounders usually look directly downward, and also the altimeter also do that. But for the imaging radar, you look at sideways. And the reason to do that is that because if you have a flashlight, you look directly downward, you get a dot. But if you look sideways, you get a pretty big swath, so that you could imaging not just a single transect, but you can imaging a pretty wide swath. And we're talking about the swath width of typically, depending on your antenna design, tens of kilometers to hundreds of kilometers. And that is why every time when you fly over just with a single pass, it's a techniques that can mapping a very, very wide area. So it doesn't need a lot of repetition to map the entire Earth. And every time when you're mapping this area at a given ground pixel, here we're talking about the SAR techniques that enabled each of the ground pixel resolution is on the order of meters or 10 meters around that size. You can get it done, but typically open available data, they don't like to give you data at sub-meter level. It's definitely possible. It's just most of the open available data, those pixel size is about 10 meter and 5 meter to 10 meter. That's the size of the pixel we're talking about. And as you can see, it's a global data set with 10 meter resolution, and it is going to repeat to do this kind of imaging over and over again. So inherently, we're dealing with a very, very large data set. And so at a given pixel location, it will reflect the echoes that is sent it out, right? And at every pixel, you receive two pieces of information. The amplitude information, and which when you put all those pixels together, give you a grayscale images. They are complementary to the optical image, given that they are working completely differently, and sensitive to different parameters of the surface. But you can kind of imagine when you look at a radar image, you will be able to identify some of the surface features like the water bodies, the cities, the road, etc. And if you have a multiple image, those amplitude image you could use for change detection, feature extraction, and a lot of the imaging processing techniques you work on optical image would also work out very well here. And also, besides the amplitude image, there's also the phase information. But very disappointingly, if you look at the phase information, it's just looks like your TV is broken, and it looks like random phase noise right there. And the reason for that is because for a radar pixel of 10 meters, microwave has wavelengths of usually centimeter wavelengths. And so when you're talking about the scatter on the surface, it's not a big tree. It's the size comparable to the radar wavelength. So you're talking about tiny centimeter level surface structures that is interacting with the microwave. And so within for example, 10 by 10 meter pixel, there are going to be many of those scatters randomly distributed inside the pixel. And your phase return is the sum of the phase from all the scatters. And because all the scatters, you have no idea what the surface, the centimeter structure looks like. So that's why you get all these random phases that's not directly interpreted for geospatial information. But interestingly, if you have another radar satellite maybe flying over the area at the same time, or maybe at a different time, it doesn't matter, right? The critical assumption is that if the surface scatter hasn't changed that much, like for example, all the scatters still remain in the same place, and this two measurement has a two phase measurement, their difference is actually can be linked to the range difference between these two SAR acquisition time. And that is essentially what InSAR is trying to look at the two radar images, identify the return of the phase from the same scatter, and use a phase difference that link to range difference, and use that mainly to infer surface topography and surface deformation. And so, to give you a more closer look of the imaging geometry. So here is a traditional setup. And for this particular setup, the radar is actually on a space shuttle. That is the JPL, NASA launched the topography mapping mission in 2000 called the Shuttle Radar Topography Mission. And so the main radar is on board on the space shuttle, right? And then it sends out the radar wave that travels along this direction. And in order to have interferometry, you need to have two receivers, right? So there is actually a 60 meter mast that stick out of the space shuttle, and so you have a radar receiver that is on board right here. So you can receive from the main spacecraft and also another receiver at this secondary receiver. In that way, you get two images at the same time, and then there is a phase difference, and that use that to infer topography. So based on this two setup, there is a way is that there is a classic setup that is means there's one antenna transmit, and then you have two receiving antennas, one at the main shuttle and one at the secondary receiver. And in this way, the range difference of this phase return would equals the range difference rho 2 minus rho 1, just without a factor of 2. But if you have two antennas that both transmit and receive its own echo, that is this ping-pong setting, and then you will have to consider that the difference of the phase actually have to account for the two-way phase travel, so there is a factor of 2 there. So that's doesn't matter really much, but it's really with this two setup, then you have a slightly different formula for how the phase difference are linked to range difference. And of course, this is for topography setup where you have two radar satellites flying over quiet data at the same time. If you have a mission for deformation mapping and you would like the same radar fly over the same area over and over at a different time, like that's what the Sentinel-1 mission is configured. And in that case, P is always 2 because you always have a two-way phase travel difference in that setup. And then I would like to give a brief idea. It's the math is actually all high school math. So our computation in the code was pretty straightforward. There's not a lot of the expensive ones, but it's the geometry that are baked in that I would like to give you a brief idea how this data, the phase difference, can be actually linked to topography. So here we have this configuration. A1 and A2 are the two satellite position when they are collecting the data, and at a given pixel P, and they have this range difference delta rho as illustrated there, right? And so what we know here is we usually know the satellite location pretty accurately. So for the Sentinel-1 mission, they know the location at a centimeter level. So you can imagine A1 and A2 are known location. And because A1 and A2 are known, that a baseline B, that's the distance between these two satellites, is also known. So those were something we automatically compute in our software. And besides that, that alpha angle is also really with the imaging geometry is known because we know where the A1 and A2 are, right? And so what we're measuring is the delta phi, that's our directly data, and which can be indirectly inferred based on that phase relationship every 2 pi or 4 pi, and you have a wavelength of range delay there. So that's our first equation. It's our actual data measurement. And so how this measurement is linked to topographic height, that's what we see as h minus z. So z is the topographic height. So we know h from the satellite altitude, and then what we're really interested in is z. So you're really, if we can solve for h minus z, then you know z, right? And so to be able to link the delta phi to z, and you will have to use the two triangle numbers here. So we use the laws of sines and laws of cosines a lot in those kind of derivation. But the idea here is this theta angle is actually really with z. You can see if it's higher, the theta would be slightly different from if z is at a lower elevation, right? And so the angle right here, is actually 90 degree minus theta, right? And so the angle A2, A1, P is actually alpha plus 90 degree minus theta, right? And so then basically using laws of cosine, you know this length, you know this length, and you know this length, and then this is basically cosine of that angle, then you have the trig identity. We use trig identity a lot, and in high school I used to be able to memorize them. Now I just use a lookup table and for that. Right, and then once you have the second equation, and then you can use the third equation once you have the second equation to solve for theta, and then you plug it in, you could get the third equation. So that's kind of the idea, but in reality, we don't actually need this complicated solve by doing these geometry tricks. You actually can have a pretty straightforward equation right here. So this is the final equation derived from the previous three equations, and it's interesting is that delta phi, that's the topography phase we could measure from INSAR, is actually can be linked to dz, that's the topography change from pixel to pixel. So we have to usually start from a reference point and then just move around a little bit to track the change. So that's the dz there. So that's through our derivation and can be directly linked together with this very complicated factor, but you can see what's in it. It's all the measurement that we know. B is the satellite baseline, alpha is the geometry angle, and also rho, like radar measurement, each pixel, you know the range directly because that's what the radar measure. You send out a pulse, you have a time return, you know the range directly. So the idea is, well, that term looks very complicated. It is mostly unknown. And also, more importantly, if it is a smaller area, that term is more or less constant. So that means when you have this interferogram formed, those fringes actually is linearly related to the topographic height. And so we will see an example. And so what you will see here is that it looks like those contour interval of the surface if you have a mountain. And so that's how INSAR works for mapping topography. And how is this actual setup for the mission? So this formula was already put in place. If you have a Google Map service and you move to every location, there's elevation, and this is from this data source. So the very first one is a shuttle radar topography mission. Now this data is available everywhere. And so the launch was the same configuration. You have a radar transmitter at the main shuttle, and then you have another receiver at a further distance. That is about 60 meters. That's how much they can do still maintain a stability, right? So ideally, you would like them to be a little further apart than 60 meters, but that's what they decided technology-wise. That's a good trade-off back then. And so there's a follow-up mission, so the Tandem X from the German Space Agency that is still in service, but the data is not openly available just because the topography is a valuable data set. So this data you have to pay to get this data access. It's a Tandem X mission, and the main difference is instead of having a single shuttle radar flying over, it has two twin satellites flying in formation and collecting data at the same time. So they need to be synchronized, and their distance is about 500 meters. So that's kind of, after all the theoretical derivation, kind of an ideal distance for achieve the best accuracy in this setup. So those are the two current setup for the existing missions. And so at least from the NASA perspective, I think they're like after the SRTM, the topography for a while using radar was being forgotten. So it has been 25 years. We don't have a new topography mission yet. So I did see that this discussion start to come back. So hopefully we will have updated topography. And it's something that is in discussion. It's, of course, I'm a radar person. I would think INSAR is great for mapping topography. And so there's also other options that is in discussion. So for example, we have a lot of optical images, and if you have collected a lot of optical imaging over the same area with a slightly different angle, the images would look so stretched or shifted a little bit, right? And based on where the same target is at a different location, and you can do that with radar imaging as well, right, using the amplitude information. And you can develop a technique called an optical stereo type of algorithm to retrieve topography. These were the technology used for retrieve topography in the Arctic region, because SRTM only goes to northern 60-degree latitude, right? And so it definitely works. And there's also laser altimeter. So what you do is you have a laser instrument, and you usually have several laser beams that is evenly spaced. As you fly over, you shoot the laser downward, and based on the delay time, and you can use that to estimate the topography, like basically using the distance to invert for topography. And then we have this radar interferometry. So most likely, I think the future mission gonna be like maybe a constellation of a fusion of those kind of techniques, in my opinion, because they all have good and bad. So for example, if this optical-based sensor, the problem is a certain part of the world is very cloudy. So 99% of time is cloudy. And it doesn't work when it's always covered by cloud. So if you're using optical sensor, a true global coverage is unlikely, just given that in some area, it's just never gonna see what is beneath this cloud. And also the optical information, so the data processing requires some adjustment in the lightning condition, and also usually will require a pretty extensive ground control network to make the true calibrated data set work. And for the laser altimeter type of approach, I would say that's probably the one that gives you the best possible accuracy. And the problem for the laser altimeter approach is as you fly over, you shoot a single laser or several laser beam down to the Earth. Each return is one measurement. And so instead of getting an image, you get a profile. It's like maybe if you have 5 lasers, you get a 5 evenly spaced profile. You have a very high resolution along track. You have a very poor resolution across track. And in order to cover the entire globe, you have to fly over the same area over and over again, every time collecting 5 more pixels. So you need a lot of repetition to to get the same coverage rather than radar you fly over, you cover 300 kilometer swath in one setup with a meter level resolution already, right? And so that's why the laser ranging, those laser surveys are typically, they are being used for maybe a regional survey or in regions that doesn't have a big changing topography. For example, the interior of the ice sheet, where the elevation is really flat and they change very, very slowly. And if your signal has a very low frequency component, you don't need to collect that many samples. If it's entirely flat, you just need one measurement to constrain what it's like, right? And so that's why this is also very useful, but it's in those relatively flat area where you don't really need that much high spatial resolution. This gives you the best accurate result. And for radar interferometry, I would say it was selected for the SRTM mission. It's kind of a nice trade-off. It doesn't really matter where you have a cloud, right? And it also gave you a very broader coverage and also reasonably resolution. The accuracy we can achieve is on the meter level, which, like when you're talking about topography, which is usually pretty good already. So that's for INSAR for mapping topography. And for most of the satellite missions now that we have openly available, they are usually designed for mapping surface deformation. So this is doable once you know the topography, like maybe from SRTM or another topography data set. Just consider the same setup. So if you have a repeat orbit radar that are flying over the same area over and over again, for Sentinel-1, that is every 12 days, and maybe with 2 satellite constellation, that's every 6 days. You can come back at the same area. So you still have this configuration. There is a baseline, that's the distance between the satellite. You need to fly back in a near frozen orbit, but you need to have a slightly different baseline. So that's kind of a typical arrangement if you have a baseline there, right? And so not only your return gonna have a topography phase, and if this ground surface pixel has moved from A to A prime, and then that will lead to additional range delay added to your signal at this location. And if we know the satellite position and we know the DEM, we can pre-compute what's the topography component is in that interferogram. We can remove that. Right, and what is left is something looks like what we're showing here is mostly related with the surface deformation that occurred between that 2 times. And here is the interferogram, I believe it's a real one from an earthquake. And here, let me is where the rupture started, and that's why we can see the fringes looks different. It's like I have this classical butterfly-shaped surface deformation map. And from the far field to near field, as you can count the fringes. And if it's a Sentinel data, every time you have the phase changing from blue to blue, or red to red, or pink to pink, that is a color scale. It's a cycle of 2 pi phase, which is translated to like half of the wavelength for Sentinel. That's 2.8 centimeter of a deformation that occurred during the earthquake. And you can see as you move closer to the fault, the fringes are denser, and that means the rate is getting higher and higher as we close to the fault. And if there is a gap in the middle, that is due to the aliasing. If your phase become changing too fast, then your sampling rate may be not sufficient to capture that. And in that case, INSAR is typically we're talking about 10 centimeter level deformation. When your signal is too big, it actually doesn't work just because you're basically having those aliasing issue. But nonetheless, in that kind of very fast moving terrain, we can use an alternative technique, basically using the amplitude data to do the feature tracking, right? And so if you moved several pixels, you could identify the same feature and do feature tracking. So that is used for tracking larger motion. And the INSAR phase is used to track a much subtle deformation. And so we have this kind of a data available since 1992. I would say some of the first critical development was actually done in the 80s after CSAT was launched, so they have some preliminary work to demonstrate this work. But the first global mapping mission was the ERS-1 that was launched in 1992, and it was a great success. And because ESA has been ever since launched a lot of missions, so they have made a lot of a contribution to the community. And we also have the JAXA's L-band ALOS 2 mission, the Terceira X from German Space Agency. So a very exciting part. Finally, I can say that the NISAR mission was finally launched last year in July. And so I'm excited about that because the NISAR data is expected to be available very shortly. I think it's going to be maybe this February, so in about 2 months or 3 months, we're going to have not only just Sentinel data, but also NISAR data to complement our observations. And we know that we also have Roselle planned in the upcoming time. So this is like a really good time for INSAR research. When I was a student, I was around here. So all the past data, pre-2010 data set, so those missions, and they tend to have a very long repeat cycles, so they only come back every 35 to 46 days, and they have data gaps. So what you're really talking about, you maybe have a 6 data set or 7 data set to do the analysis. But now, instead of having 6 to 7 SAR data set, tens of interferogram, you start to have hundreds of SAR images over the same area. Maybe like every year you get about 30 images from one path, and you have a multiple paths, and then you do the pair, so you're talking about 10,000s of interferogram. And a lot of those machine learning work, like that's where it's getting excited. It doesn't really work if you only have like a 6 data set, right? But things start to get interesting when you have tens of interferogram, 10,000s of interferogram. So that really opened up a lot of opportunity for computing, for machine learning here. So give you an example of an interferogram. So this is ALOS interferograms. This is one of the earlier mission interferograms. So this data was acquired around 2007, and so you can see this single image already covers a substantial area of the Hawaii Big Island. And to give you a sense, the Sentinel-1 data is typically cover a much larger area. So here the swath is about I think 50 kilometer-ish in that image. For a typical Sentinel-1 image, the width is 250, and it's 2D, right? And so usually the image we're talking about is a much larger image. But nonetheless, the information that are contained in those images more or less the same. So here, what you can see here is the reason we call this one is that it captured an interesting volcanic event that called it the Father's Day event, because on the Father's Day of 2007, there is a rapid deflation in this Kilauea caldera, and then the volcano, the lava that kind of traveled through this east rift zone, and they pushed the rock open, and so you can see some of the features here. And if you pay attention, the color scale is actually reversed. So here is a deflation, here is like a pushing open, and a little bit of inflation here, and so then you can see some kind of eruption that is occurring right here over this region. So this event is clearly imaged by the ALOS data. And for ALOS, it is an L-band sensor like NISAR, and so each phase cycle when you see green to green is a half of the wavelength of L-band, 24 centimeter, so it's about 12 centimeter of a motion along the radar line of sight here. And here you can see there are several fringes, so that's cycles of fringes. That means it probably has tens of centimeters, like 24 or even more deformation along this east rift zone. And besides those deformation, you can also see some other features like this reddish color along the coast. So I will talk a little more later, but these are not the actual real signals. So that's kind of the part, like INSAR is great, it contains deformation signals, but it also contains other sources. Someone would call it a noise. Some people might think it's interesting, but in this particular case, it's because of this coastal region, there is a fault system, there's a big cliff right along those areas. That's a Helena fault system. So the water vapor from the ocean was trapped right around that fault line. And then you can see those are the area with extensive water vapor. So there's more atmospheric delay, that centimeter level atmospheric delay signatures on the tropical island. So this is like a warm, humid environment, in which case is really prone to tropospheric noise. And so also you can see some fringes hinted kind of in this larger volcano Mauna Loa. And this is because when you have those tropospheric delay, when you have a huge elevation drop, and then the path would be different. So that also has a stratified tropospheric component. So for this particular case, that's one of our primary source of the error. And here in this area, you can see the face is not as clean as the other area. And this is mostly because this is a rainforest area. If you have been there, it's beautiful. And when you have some tree growth between these two soil acquisition, it kind of violates that fundamental assumption. All the surface scatter has remained stable, right? So in the vegetation area, they're constantly change a little bit. So if the change is too much, it will decorrelate your signal a little bit and add some random noise. So L-band is typically more like less prone to this, but you can still see a small, slightly degraded quality here. But for C-band, this kind of vegetation decorrelation issue that essentially turns your phase measurement into spatially random noise, and it's going to be more obvious. So here is a summary. So we can link our phase difference that's directly measured from radar image to topography or deformation. But because of the relationship between the two are slightly different, and you can see when you use SAR for mapping topography based on this sensitivity analysis, the accuracy you could achieve is on meter level or 10-meter level. So there is usually an error term absolute difference error and also relative error. So for the relative error, we're talking about something like 5 meters, right? And so it's a meter level accuracy for topography, and for the displacement, because you can directly link each of the phase cycle to half of the wavelengths, right? And so that's why your sensitivity is usually on the order of centimeter to millimeter level, given that the microwave expand 3 centimeter wavelengths and the L-band 24 centimeter wavelength. So most of our data was in between these two range. So they're sensitive to centimeter level to millimeter level motion. Centimeter if you have one image, millimeter if you have a redundant amount of data set. And so another important thing we would like to mention is that also through this processing, what we are measuring is the phase number. And if you're talking about a phase from a complex number, your value can only go from 0 to 2 pi, and then it's wrapped back, right? So our phase measurement, when you're seeing that image, when we're talking about blue to blue, red to red, it is a difference of 2 pi. And so our actual phase measurement, what we would like to track from one pixel moving along one transect, may grow like this. So this is, in reality, it can be any kind of a continuous function. And if there's a difference in the phase, there might be even jumps, right? And so in reality, maybe our phase is like that, but our actual measured phase is this wrapped phase here. So once it reaches 2 pi, it will suddenly shift back to 0. So we have this circular color scale, and that's what we will see in the lab session. I define a circular color scale that is better for visualize this kind of a data set. The idea for the circular color scale, you want a kind of a smooth transition between here and here. So almost like on both sides of the color is almost identical, so that when you displace the data, it looks seamlessly from one cycle to another. But the problem for this wrapped phase style give a lot of difficulty for geospatial interpretation, because people, when they study earthquake deformation, they don't want to know just between this and this there's 2 pi. They want to know from like far away from the earth to the center how much the largest deformation is, right? So they would like to know is the actual difference between here to here, rather than how many cycles you have. They can count the cycle manually and do that, but it's not going to be doable if you have thousands of images and you want to do that automatically. So this itself is actually a very, very interesting problem, because if you think about it, it is like you have this noisy wrapped data, right? And what you're really trying to solve is linear ambiguity at every pixel location. And so you can only add 2 pi, 4 pi. You're missing this an integer ambiguity in every pixel, and you would like to solve that at all locations and simultaneous to reconstruct the best possible reconstruction of the phase. So that's a integer ambiguity problem, harder than the least square problem, and so it's NP hard. But luckily, we have a guy who actually write a software using C, works reasonably well. So I use that many, many times. It's part of our integrated processing tool. It works better than I counted myself. And so that's what I can say, right? And well, people are still improving it, but I read the thesis. We're very happy with that. So just be assured that there is a very robust software that allows us to do this. And so, let me see. So, sorry, so this is what the actual face and the wrapped face looks like. And the unwrapping basically recovers that. And I'll give you an example of what the data looks like wrapped and unwrapped. So this on the left is the interferogram we will typically get, right? And so you can see in the middle there's a masked out region, perhaps because of poor phase quality due to aliasing. But most likely you captured this butterfly feature that is typical from earthquake rupture. And we can manually count the fringes, in this case, because the face is clean. And in area where your phase quality is low, sometimes you might have some ambiguity, but this is the unwrapped data. So basically, you're starting from maybe far away at 0, and then they're just counted at a given location how many cycles of phase that it has gone through. And given that phase, all you need to convert to line of sight displacement is to divide it by 2 pi times half of the wavelength. So on the right is in radius with phase, and all the numbers within minus pi to pi. On the right is a line of sight deformation, and it can go to a very large number if you have a very large deformation measurement. So these are pretty much like the theoretical foundation behind the software. And on the second session, I'm going to provide a link for a book. So I worked with a group of authors led by David Sandwell, kind of just go over those derivation details behind the scene for the community-based radar processing software in a more detailed way. But I think first level, we try to cover everything here. And besides that, for the deformation analysis, I would like to also cover some of the common noise. And so INSAR people, especially in the early days, I taught many people using it. They got very excited about it, and then they used it. And the first experience usually, like for their study site, it doesn't work, and they get very doubtful about how this works. So the idea is always work, but the difficulty here is in a lot of the cases we're dealing with very low signal-to-noise ratio. Not everything will lead to tens of centimeters of deformation. That's typically what we're talking about, earthquake, right? For earthquake, you don't really need much beyond forming a single interferogram. You can see the fringes. We have tools to unwrap it, and that's a displacement field you can use for deformation analysis. So that's a very high signal-to-noise ratio. But if you're talking about like a surface deformation, maybe from a silent earthquake, which maybe only the geophysicists call them an earthquake, that leads to deformation of like 8 millimeter, right? And so no one will feel it, but it has an important scientific value of it. And also sometimes when you have those aquifer pumping, that leads to maybe a seasonal signal of 1 centimeter or 2 centimeters, right? That's not well above the earthquake cycle. When you form an interferogram, you just won't be able to see the signal as the first thing in front of your eyes. You wouldn't see those beautiful fringes. You see a lot of things, and so those were the error source we're talking about here. But luckily, the whole idea is if you have a 10,000 of interferogram, each of these errors, they have some unique characteristic in space and in time. So in some way, they look different from the signal, right? And so if you know what you're looking for with some prior information, you can design an algorithm to separate these things. So, and here I would like to just go through this error because the difficulty, there's not unique recipe because those errors are coupled in different ways in different regions. The tropospheric signature in Hawaii is very different from like a high plateaued dry desert area, for example. So, and the vegetation cover is different. So you have to kind of know what you're looking for, and based on the characteristic of the error in a particular site to design maybe a machine learning algorithm. We have some limited success on that in the past couple years to separate the noise. So you can see this very long measurement. After you remove the topography, this is our phase measurement that we hope is linked to deformation. That is our first term. The line of sight can be linked to phase by this factor of 4 pi divided by lambda. Here we have the 4 pi here because we have to account for the two-way travel we talked about in the beginning. Now we have this DEM error because in order for INSAR mapping deformation, you have to first remove the topography component. And so if you have made a mistake in your topography map, that will lead to a residual here. And we have the atmospheric error that is mostly due to the troposphere and the ionosphere. And also we have the orbital error. And that's more common for the earlier missions. So sometimes when you start here, you might think your orbit is here, but over time it's diverged a little bit. And you can see that kind of signature in the data. Luckily, I think the Sentinel, like over that 20 years, the people who do orbital determination seem to did a great job. I see those kind of artifacts less and less now. And we also have this vegetation decorrelation, just inherently if surface really has changed, it doesn't work. And also when you do the unwrapping, you have some error and some other secondary error like a soil moisture, things like that. So this is what the orbital error looks like for the early data. So this kind of a correction is no longer needed. Is that here on the left is an ALOS interferogram. When we know this area, you can see the phase is kind of traveled from a light pink from the upper left region to blue again. So that's about a cycle of 12 centimeter. But this area, we know there is no 12 centimeter deformation, so this is definitely not noise signals. So what is happening is this orbital divergence that happened that gave you this kind of a ramp-like signature. And so, but the idea is if you know this is a ramp, and if your deformation doesn't look like a ramp, you can just estimate the ramp and remove it, and that's what is showing on the right. And now, you might not know, but I have done the analysis. There is a very faint yellow over this region. So that is actually the real signal from the aquifer pumping and recharge. So this is a recharge season, so you see a minor surface uplift there. So it's only when you are able to remove this higher order errors, then you start to see this very subtle deformation, not just in one image, but they will be consistently showing up in many images. So that's when you know it agrees very well with the in situ measurement. And also the DEM error, so these are also common in early days when your DEM is not good. So these are two images that it was processed using the same software, and the only difference is the topography data that was feeded in for removing topography phase is different. And clearly, you can see when you see that this DEM has a lot poor quality because you see all those artifacts that is not showing up in the other DEM reproduced interferogram. So I think this technique is actually very sensitive about the DEM error. I think it's like if you're off systematically by a bias, it's less sensitive to it since we care about the relative motion. So that got canceled. But if your data is incoherent, for example, you might have a DEM was merged from two different data sources. You can definitely see that. And they're not calibrated in the same way. So that's what we can use. But nowadays, I think our DEM quality is getting pretty good. And either the Arctic DEM in the northern latitude or the SRTM data in the mid-latitude and the equator region, this, unless you have a very steep terrain, it's not going to be a big deal. And also this ionospheric artifacts, right? And so this is typically worse in long wavelength data. For example, this is going to be a big deal for NISAR and also for the ALOS data because the ionospheric delay is inverse proportional to the frequency. And so when you have this ionospheric delay, so the fringes, like those kind of fringes, and here you see the decorrelation is because the delay is so much, it actually moved your radar pixel by a couple pixels. So this is a pixel offset map here. And when your pixels are no longer co-registered with each other, you start to no longer have a coherent phase. So luckily, we can actually start to estimate and remove the ionospheric artifact, similar to what we did for GPS. So you have a slightly different frequency, so you could chop your data into two sub-frequency band, and because the ionospheric delay is really with the frequency, so they will be slightly different, and everything else would be the same. And based on the phase difference between these two sub-band, you could actually correct and remove that. So while the ionospheric delay is typically pretty bad for L-band data, especially right now we're in a active solar cycle, and so we have ways to mitigate that. So that's, but nonetheless, I think this actually means if you're from the ionosphere community, so with all those interferometric map, you could actually use this artifact to invert what the total electron content looks like spatially. And so that's provide another way to probe the atmosphere. And also, finally, the troposphere, we already talked about that and earlier in that Hawaii map. So this is a noise that is happening everywhere due to the temperature, water elevation change, and water vapor content difference. And it significantly vary. And my experience in warm and humid areas, this tends to be bad. Like you can get up to 10 centimeter of noise just from the tropospheric variation. And like you can think about like you have a bigger cloud in a local area and you don't have that rainstorm in another area. So you can definitely see those phase signature from that. And the way to kind of correct this kind of tropospheric noise, there are two ways. So the first way is most of the software, they have ways to automatically pull in the weather model and trying to, based on the weather model, to predict what the tropospheric noise looks like in your data. And my experience is that it's usually very good at capture the large-scale tropospheric delay structure, and we're talking about weather model has a kilometer-wide resolution, right? And they might not update it adequately, maybe 6 hours. So they might be able to capture some of the more large-scale structure that doesn't change too fast. And also, those weather models are usually being solved together with the GPS network, because the GPS receiver you can actually see for the zenith delay at that location, and they served as like a upscaling, like they can interpolate in between the weather model to increase the resolution. So we have some relative success in regions where you have a bigger topography, because those kind of areas, the stratified component, the weather model is more predictable. But what is left is sometimes you have those turbulence noise, like those ones in the coast. They change it too fast. And also maybe they have this very small local scale. You have like a weather turbulence at maybe a kilometer scale. So these things are not usually adequately captured by this existing atmospheric correction. But the way to deal with this kind of data is usually leverage the fact that now you have a many acquisition, and you're thinking of those local turbulence noise changing rapidly. So like between 6 days, whether you rain or not, they are not correlated, right? And so you treat them as random noise, and you can use an optimization method to solve for the deformation from those turbulence noise. And finally is the vegetation decorrelation. And we mentioned earlier, for the SAR image, you mostly see this randomized phase, but for INSAR, you start to see these nice fringes that looks like a signal related to topography and deformation, right? But the unfortunate thing is if surface has changed a lot, maybe someone has worked on the road, gave them a new surface, or maybe you have an agriculture area, like day 1, you have a bare land, day 2, you have just all the cornfield grow together, right? The surface has changed, and in that case, your interferogram will return to what it looks like on the left. So we can actually access the quality of our data, whether the decorrelated or coherent, right? We can only use the coherent data for analysis directly from data. And the formula works as follows. It looks very long, but I would say a lot of the data scientists would probably recognize it. It's a similarity measure. So what this formula says is how are we going to be able to access the quality is you go back maybe at a given pixel location, you draw a small box, let's say maybe 5 pixel by 5 pixel box centered around here, and you're calculating if all the phase looks consistent, which means they are spatially coherent. In this case, if they are all blue pixels, they are very similar, right? And so then your correlation value is 1. And in another location, like maybe like here, you draw a box. And if you look at all the pixels within that box, it looks like random. They are not predictable. And in this case, if they are completely random, your correlation is 0, which means they're not similar at all. And in some area, like here, if you draw a box, you might say, well, there is a little bit of a noise, but overall they are pretty consistent, and then you get something maybe in between 0 and 1. So this long map, so this is something we automatically calculated along with the interferogram as a quality measure called a correlation map, is indeed just like a similarity measure derived directly from data. And here is an example. This correlation actually embedded a lot of useful information from interferogram. If you're interested in change detection, for example, wildfire mapping or flooding detection. So here is a interferogram's correlation map, as we say, the correlation ranging from 0 to 1, which means yellowish color, greenish color is very good correlation, coherent. 0, there's a blue color, pink color, a relatively low correlation. And for one-day correlation, you can see most of the area on the land is highly correlated. This water surface, their waves are changing within the time scale of a second. So even over 1 day, the water surface would be decorrelated. But over the land area, you see, especially in the mountain area, things are mostly maintained. There's a little bit of decreasing correlation in this agricultural region because of the vegetation. They tend to change more rapidly. But over 3 months, you can start to see, even on the land, there is a significant drop in phase coherence due to the vegetation growth in the sandy area. But in the mountain area where you mostly have rocks, the correlation would maintain. So this correlation measure is a way for you to basically detect where things have changed and how much it has changed. So, which we have successfully used that for wildfire fire mapping and for also just to find regions with rapid change. And so the total correlation, so there are some extensive theory about what can cause a decorrelation. Most likely what we're seeing here is this what we call the temporal decorrelation, that is due to the surface has changed. But if you have a slightly different imaging geometry, that would also lead to something called a spatial decorrelation. That usually happens in very, very steep terrain like Mount Everest, where you just look at that mountain cliff with a slightly different angle, they will look like the incidence angle changed quite a bit, and that will also lead to decorrelation. And finally, we want to mention this kind of decorrelation is linked to how much change has happened on the Earth. So if you have a longer wavelength measurement like L-band NISAR or Roselle, and then they can tolerate more change and still not lead to decorrelation. So this would be some similar land phase at a C-band interferogram, L-band interferogram, P-band interferogram. So one of the advantage of L-band is that usually you see fewer fringes, it's easier to unwrap, and also it's less, works better in the vegetated area, and just because it's less prone to the decorrelation issue. So I'm at 10, and I think that's the end of my theory session. We're going to have a coffee break, I believe, right now. But after that, I'm going to have a hands-on session. So these are mostly theory, and we already have all the software. Most people don't have to know the detail. But in the hands-on session, I would like to briefly go over the workflow in the actual software we developed. So right now, I'm a contributor for the GMT-SAR software. And so we're interested in integrate some of the Julia utility into the software and in the future. And so I want to talk about the workflow in the existing software, and also give you some sample radar images that, and also talk about the challenges. And I'm very new to Julia, so I'm very open to some suggestions how I can make it easier for people to use it. Thank you. I think we're done for now. Yeah, yes, I'm happy to take questions, of course. Yeah, we can do that in workshop. I think once people see the interferogram and work on the data format, it will be more obvious what they were looking like. Yeah. Yeah.
Thank you, ma'am Anchen. Now we have a coffee break of half an hour until 10:30.